Modern large language models are built on staggering amounts of text. Systems like GPT-4 are trained on billions of words, digesting vast swaths of the internet to form their underlying knowledge base. Because of that massive training data, these models excel at what developers call zero-shot prompting. You can ask an AI to summarize a topic or generate code it wasn't explicitly trained to handle, and it will draw on its pre-existing knowledge to give you an accurate answer right out of the gate. But if you try to integrate this into real software, you hit a massive roadblock: statelessness. Out of the box, an LLM has complete amnesia between queries. If you ask it who created a software package, it gives the right answer. If you follow up with "show me a video of him," the model suddenly has no idea who him is. It fails at basic co-reference resolution because it forgets the previous interaction the moment it ends. You might think the fix is easy. Send your entire user history and your company's database to the model every time you ask a question. The problem is the token limit. Language models have a strict cap on how much text they can read at once, and an enterprise database simply won't fit into a single prompt. For a brief period, this created a severe bottleneck in the industry. To get around these limits and build custom AI tools, developers thought they needed to fine-tune custom models from scratch, a highly specialized process requiring a PhD in machine learning. That is the exact gap LangChain was built to fill. It operates as an abstraction layer, handling all the complex memory management and data routing behind the scenes. Now, standard software engineers can treat AI as a modular tool, building highly complex applications without needing a machine learning degree. The first step in this abstraction is moving away from manually typing out static instructions. Instead, developers use prompt templates. These act as reusable code wrappers with designated placeholders. Instead of writing a new prompt from scratch every time, the user's specific request slots perfectly into place inside a pre-formatted structure. Once that template is filled, it moves through what's known as the LangChain Expression Language, or LCEL. Using a simple pipe operator, the formatted prompt flows left to right, directly into the language model to generate the final output. Because this pipeline is highly modular, the AI itself is completely decoupled from the surrounding architecture. If an engineering team wants to move away from OpenAI and use a local open-weight model like Ollama, they can use so by simply swapping out that single node in the code. This setup grants developers complete operational freedom. Instead of being locked into a single vendor's ecosystem, teams treat the language model as an interchangeable commodity within their own software stack. That modularity also provides an elegant solution to the token limit and data isolation bottlenecks. It's a framework known as Retrieval Augmented Generation, or RAG. It starts with data ingestion. LangChain uses document loaders to pull raw, unstructured information, like taking a Wikipedia biography of Elon Musk, and standardizes it into a plain text format that the system can actively read. Because of the model's token limits, that biography is still too large to read all at once. Text splitters solve this by breaking the ingested document down into smaller, semantically related chunks. Next, these individual chunks go through an embedding process. The text is mathematically converted into vectors and stored within a vector database. This organizes the information based on semantic meaning, placing related concepts closer together in a 3D coordinate space. When a user asks a specific question about the biography, the system doesn't try to read the whole file. It performs a similarity search across the database, retrieves only the 2 or 3 relevant chunks, and feeds those specific details directly into the language model. By fetching only the precise context needed at the exact moment it's requested, RAG bypasses the token limit entirely. The model gains selective access to massive private datasets, and the engineering team never has to retrain a custom algorithm. Once you solve memory and data retrieval, you can push beyond simple chat interactions and build AI agents. This means taking the LLM's natural reasoning capabilities and equipping it with executable tools, like the ability to search the web, query a database, or use a calculator. To architect these complex agentic systems, developers use a mathematical structure called a graph, powered by a library called LangGraph. This relies on a network of nodes and edges. The nodes are Python functions. They do the actual computational work. The edges serve as the conditional logic. Once a node finishes its task, the edge evaluates the output and decides exactly which path the application should take next. Crucially, this entire graph revolves around its state. The state acts as a central, localized memory bank that every node reads and updates. Because this memory persists, developers can implement advanced cyclic loops, where an AI agent critiques its own work and loops backward to try again until it gets the right answer. This distribution of labor changes how generative software is built. Instead of chasing the perfect model, developers are focusing on the system's architecture, spending 60% of their time on flow engineering, refining the steps and state machines that define an agent's behavior. LangChain has changed the developer's role. Standard engineers are no longer writing strictly linear code or treating AI as a mysterious black box. They are architecting intelligent state machines that make generative AI tools accessible to every developer.